Previous videos, linked in the description below, use kinetic theory to examine reactions as collisions between molecules and to derive the experimentally determined rate laws using that theory. In this video, the concepts of kinetics will be used to look at extra reactive properties called transport properties. They are viscosity, diffusion, thermal conductivity, and electrical conductivity. At first glance, these four properties seem to have absolutely nothing in common, but surprisingly, they all follow the same basic law. That law can be written as F is equal to minus K times A times the upside down triangle is called a del, which basically means a change in some set of states. In this case, A is the cross-section of whatever pipe or conduit is used to carry a property. K is some sort of intrinsic constant. F is what's known as a flux, the flow of some property through time. For viscosity, that property is momentum. Diffusion is the flow of mass through time. Thermal conductivity is the flow of heat through time. And electrical conductivity is the flow of charge through time. The del is a gradient. How some property beta, which determines alpha, changes over distance. For viscosity, that is a change in velocity over distance. Diffusion is a concentration gradient across a distance. Thermal conductivity, you have a temperature change across a distance. And in electrical conductivity, you have a voltage drop or a change in potential. All four of these properties are kinetic in nature and deal with the kinetics of transport, where once again, you have some property alpha that is a function of some property beta. So a very simple question. What is the flow or the flux of alpha? How does the concentration of alpha change with time? In order to measure this, first of all, you need some reference plane and define that you are looking at the flow of alpha in some y direction. In this case, the change in alpha is going to be the beta of some n particles moving from left to right minus the beta of some n particles moving from right to left. Statistically speaking, these should be equal to each other. If you do not have any external force, the number of particles moving left to right and right to left are going to be equal. And from kinetic theory, that's going to be 1/2 the total number, the density of the particles times their velocity times the area of that plane x0 with time. So the change in alpha is going to be that times the beta of the left moving particles minus the beta of the rightward moving particles, which is equal to dB. And then you can do a slight change that dB is equal to dB dx times dx. And again, from kinetics, you know the mean free path. Since these particles are not necessarily moving in a straight line, they could be moving at an angle, the average distance traveled is going to be 2/3 lambda. So dx is going to be minus 2/3 lambda going backwards plus 2/3 lambda going forwards, or minus 4/3 the mean free path. So in general, you get the following rule for transport. The alpha dt, which is your flux, is going to be equal to 1/3 the mean free path times the density of particles times the average velocity of the particles, which is some intrinsic constant to the system, times the change in beta over dx, which is your gradient, or the general rule minus some constant times the area times the gradient, del. Looking at the properties one at a time. Let us first look at viscosity in detail. The laminar flow of a fluid through a pipe of area A, where once again there is no turbulence, it's laminar, everything's moving in a straight line. So I get some pipe of some area A, where x is the direction of the width of the pipe, and the fluid is traveling in the y direction at some velocity. In laminar flow, the layers will slip past each other, where each one exerts a friction upon the next layer in such a way that you get the highest velocity in the center, and at the boundaries, the velocity goes to 0, which is called the no-slip condition. This is seen in everyday life. If you've ever run a fan, you'll notice that the blades on the fan are always dusty, regardless of if the fan was running or not. So, according to kinetic theory, as shown previously, in this case, the alpha we're looking at is momentum, the mass of the particle moving in the y direction, over a velocity gradient in the x direction, where the particles in the center are moving faster and they move slower towards the boundary on either side. So simple substitution says the change in momentum is going to be the 1/4 n times m over v now, times the mean free path, average velocity, pipe diameter, difference in velocity times the change in temperature, change in time rather. A couple of simple substitutions. By adding mass from momentum, the number of particles times the individual mass divided by the volume simply gives you density. Also, the substitution dvy is equal to dv in the y direction dx times dx. Knowing that dx is minus 4/3 the mean free path leads you to a flux of the change in momentum with time is equal to minus 1/3 the mean free path times the density of the fluid times its velocity, area times the velocity gradient. This theoretical construct is actually the statement of Newton's law of viscosity, where the flux is equal to minus a viscosity times the area times the gradient. So essentially, for a gas, the viscosity is equal to 5/16 pi to the half, mRT to the half, Avogadro's number, times the diameter of the molecule squared. This is for a perfect gas, and again, the theory derives the actual results from experiment. Moving on, diffusion. In this case, alpha is your concentration, where we'll keep the same convention that B is the solute and A is the solvent. And beta is the mass of the solute B. So you get the flow of particles, dNB dt, is equal to some constant. That constant is called the diffusion constant, where dBA is the diffusion of B through A. dAB would be the diffusion of solvents through the solute B, and in any given solution, these two are not going to be equal to each other. That's the experimental result. Theoretically, at infinite dilution, the diffusion coefficient is simply the ratio of the force moving the particle forward divided by the friction that is trying to stop it. For an individual particle, the energy that particle has to move is always kT, Boltzmann's constant, times the temperature. The friction depends upon two things. It depends upon the viscosity of the solvent and the size of the solute. So your friction component is 6 pi times the viscosity of the solvent times the radius of the solute. Either a thicker solvent or a bigger solute will diffuse slower. This is the Stokes-Einstein equation, and it is used for determining diffusion in liquids. You can use this to actually get experimental results. If you can find the mean squared displacement of a particle, such as through a viscosity experiment or a diffusion experiment, that is always going to be equal to 2 times the diffusion coefficient times the amount of time that you've been observing. So for liquids, you have dBA or dAB, the diffusion coefficient. From the kinetic theory of gases, for a single component gas, the diffusion coefficient becomes approximately 1/3 the mean free path over the velocity, specifically 3 pi 16th times the mean free path times the velocity. So for a perfect gas, the diffusion is as follows. You got 3/8 pi to the half, RT over the molar mass to the half, 1 divided by the diameter of the gas molecule squared times its concentration, N over B. This is the diffusion for a perfect gas, and once again, it matches what was determined previously because diffusion occurs and is powered by the entropy of mixing. The third transport property, thermal conductivity. From the kinetic theory, in this case, the alpha is the quantity or the quality that's being transferred across an energy gradient. If I look at the condensed state, dq dt is going to be equal to minus some thermal conductivity constant times the area over a temperature gradient dt dx. From general chemistry, you also know that dq is the mass times some specific heat times the change in temperature. Therefore, the specific heat of any given solution is going to be its minus its thermal conductivity times the area of the flow divided by the density. In gases, you have the dE dt times dE is equal to dE dt times dt is equal to dt over dx dx. The reason you do this, why is the change in energy with temperature important? Because thermodynamically, the change in energy with temperature is the change in the internal energy from thermodynamics, du, and since you're talking about a single particle, divided by Avogadro's number. The change in internal energy is the heat capacity at a constant volume. So for a gas, the flux of heat is determined by the heat capacity and the temperature gradient. Where your constant, your thermal conductivity, is the density of the gas, the velocity of the gas, the heat capacity of the gas, its mean free path, divided by 3 times its molecular weight, noting that all of these particular terms are specific to any given gas, which is what makes this an intrinsic constant. Electrical conductivity. In this case, your flux is charge across a potential gradient phi. So you get dq dt is minus some conductivity kappa times the area of the pipe, d phi dx. Some substitutions from outside chemistry. The flow of charge with time is the definition of current in amperes, symbolized by I. d phi dx is a voltage drop. So I can rewrite this that the current is equal to the integral minus the integral of some constant times the area, d phi dx. dx is simply going to be x, or the distance that the material moves, or the charge moves. So I can rewrite minus delta phi is equal to the current times the distance divided by the conductivity times the area. Essentially, at this point, I have the change in potential, which is a voltage, is equal to a constant, times the distance traveled divided by the area times the resistivity, or divided by the conductivity. You get V equals IR, which is Ohm's law. So in this case, you have three disparate properties, all of which involve motion, which means all of which generally obey the same law and are connected with each other. In the next video, also linked in the description below, we go into Ohm's law and electrochemistry in more detail. Thank you very much for listening. I hope you found this useful.